Good evening, everyone. Welcome to today's section on interactive section on digital VLSI testing. So this is the week 1. So we will start with the basic introduction on the digital VLSI testing. So this section we will keep it as an interactive section. So you can turn on your mic and ask the doubts. And also if you have any doubts, you can just post it in the chat box. So first let's start. To begin with, we will first start with what is the basic, like the ASIC design flow. So the ASIC stands for the application specific integrated circuit. Uh, so we have like two types of design where we say ASIC and FPGA based designs. So ASIC stands for application specific integrated circuit. So this design in the ASIC design flow, first we have the what are the we note down what are the design requirements, and then we follow what are the specification required for it. With that, we give the RTL level design. In the RTL level, we perform the functional verification and also RTL level DFT. Yes. And followed by this is the front end flow. In the back end, we perform the synthesis and we obtain a gate level netlist. In the gate level netlist, we add some circuitry which will help to do the testing. So that is known as the design for testability. So this is the place where we have the testing portion in the ASIC design flow and also at the RTL level. Further, we have the placement and routing step, followed by the clock trace synthesis and the power distribution network. And here we perform the verification of the design. And finally, we obtain the GDS2 format file, which can be sent to a foundry for fabrication. So now here we have two steps like verification and design for testability, DFT. So now let's just see what is the basic difference between testing and verification. Can any one of you answer? Okay, so verification is used to identify the design bugs or any is there any mismatch in the design, and testing is used to identify any of the defects in the manufacturing step. Manufactured IC. So this verification step is for the design and the testing is for the manufactured ICs. Yes, recordings will be provided after the meet, like it will be uploaded in the YouTube. So now, just briefly describing what is the testing. So I have an IC which is now say fabricated. Now I want to know whether this IC is having any defect or not. So for this, we need to perform the VLSI testing. With this, we have a term called defect, which we is at the physical level at the manufacturing process, which we model as say as fault, which propagate as error. So now here we have some three terminologies. So we will briefly describe these terminologies. So firstly, what is a defect? I am just giving some basic one of the example. So When we have a difference in the hardware, which is implemented hardware and the intended design, we call such difference as a defect. Now, if we consider a bridging defect or an oxide breakdown, like bridging defect, here you can see a material which is bridging between these two nodes. So this is known as the bridging defect. Now here you can see some material has come here. So this is also forming some bridge but between the multiple lines. So it's a large amount of material, so it's shorting more than two lines. And here we can see it is shorting between the two nodes. So this type of where a material is shorting, which is going to alter the intended functionality, is known as bridging defects. Now, as we said, defects can be modeled as faults. So the representation of a defect at a logic abstraction level of a design is a fault. So now initially if we said this line and this line there is a material. And now if we see at the logic level, these two are getting shorted. This is modeled as a fault. So now if I consider for an example for a fault, consider that this line here a VDD line is coming, let's consider, and a line. Now there is a similarly some material is formed which is shorting both these lines, forming a bridging defect. Now if we model this, we can say that this line is going to be always stuck at VDD. Whatever the value of A, the line is always going to be at VDD. So such modeling is known as faults, where at the logic level we have modeled this line bridging to the VDD has stuck at VDD, or we can also call it has stuck at one fault. So now this, if it is say I apply a okay, how I apply a 0 here, I apply a 1 here. Now the output should be 0, but because of this fault, it is coming as 1. If I consider this has the fault free value by the faulty value, now you can see there is a error in the output. So this is called as the error, and this modeling is called as the fault model, and where this material, where it can be a physical defects like this, is modeled as a fault and leading to an error. So error is the wrong output by a defective system. So now one of the fault model, as we have said, is the stuck at fault model, where a node is permanently stuck at 0 or permanently stuck at 1. So now testing during the VLSI life cycle is like we have a circuit under test. So we need to apply certain inputs to it, say from 0 to 10, and we obtain certain outputs. We analyze this output, and this output we call as the response. So let's say the output response, and we analyze this output response and say whether it is a pass or fail. Now for this input, we need a test stimuli. So the testing is performed at various stages. So if we perform at the fabrication stage, we call it as wafer test. Say we have a wafer, if we can use a probe here, measure it So at the wafer level, we can perform the testing. After, at the packaging step, we can perform the packaging test. So package test. At the quality assurance, that is the final stage, we can perform the final test. So testing is performed at each and every steps. So we have something called as yield. Yield is the number of uh, acceptable parts divided by total number of parts. That's it. So the yield loss can be of two types, which can be due to random or process variations. So with this, I think we can go to the fault model. So if we consider there are two types of fault models, so multiple fault model and single fault model. So if I draw one small logic gate level diagram, considering this, so here we can assume that any one node is having a fault, or the next assumption, valid assumption, can be a multiple node having different type of a fault. So what can be a type of fault? Generally, if we consider stuck at fault, it can be either stuck at 1 or stuck at 0. So two types of fault types. And what are the fault site? If we consider this, here there can be a fault, here, 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 here.
Hello, ma'am.
Yes.
Hello, ma'am. Can you please explain a previous slide? I didn't understand. Yes.
Yes, this I just briefly described. Like we have any circuit, we need to have some set of test stimuli which will be enough to, like, which will be required to test this circuit under test. We apply that to the circuit under test, we obtain some output, we use a response, this response, and analyze it to say whether it is having any fault or not. So at every different stages of the VLSI, once the chip is like fabricated, after fabricated means at the wafer level, after taking it, we take one die and then do the packaging. After packaging, then at the final stage, after the in the quality assurance, that is the final stage, we again perform the testing. So at different stages, we are performing the testing. And yield is just one concept, just I wanted to write the formula. It is the number of acceptable parts divided by the total number of parts fabricated.
Okay, thank you.
Yes. So now if I consider just this as the one of the logic level circuit, so we can see that the possible fault sites are 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are total 9 possible fault sites. So if we take n as the number of fault site, where fault site is a location in a node, like a node in the circuit, which has the probability of having a fault, and we consider say k, which are the fault type. So if we say what is the fault type, if we consider a stuck at fault, then there are two types of fault types. Either the node can be stuck at 0 or the node can be stuck at 1. So with this, we know that number of fault sites for this are 9. If we consider there are just two types of faults, stacked 0 and stacked 1. Now there are two possibilities. Either I can assume just this, say this node 6 is having fault, or I can assume a combination of node is going to have the fault. So we have two types of fault model with this assumption. So as multiple fault model or single fault model. And now if we have multiple fault model, then the number of such multiple faults. So there can be various such combinations. So the multiple fault will be k plus 1 to the power n minus 1. So the each fault site is going to have 1 to k faults. Like now for our example, it's 2. And this minus 1 is just to remove the fault free combination. And now if we assume that we have a single fault model, then the number of faults is k into n. So now you can observe if we have here in our example itself, it's like 2 plus 1, 3, 3 raised to the power 9 minus 1. So we have a huge number of combinations of multiple faults possible. And if we consider k into n, that's 9 into 2, it's 18. So we with this we have assumption that the single fault model is giving a good coverage. So good, if we have a good single fault coverage, it is generally like sufficient, and it implies that it will give good multiple fault coverage also. How to find the fault type? That is, with this assumption, we will in after this we will assume that we are going to have a single fault model. So after this, it's like we will assume that now this circuit we will perform the analysis and see whether we get a good coverage for single fault model. So it will imply that it is going to give a good coverage for the multiple fault model also. And so now with this, you can see that now for this small circuit itself, there are 9 fault sites. Can we reduce this now further? So first thing was we had multiple combination. We reduced it and said that single is sufficient. From now at the single itself, we have so many fault sites. Now can we reduce that? That is our next step. So we come to a concept of equivalent faults and fault collapsing. So here we come to two concepts of equivalent faults. If you see, it is mean to say that like one or more single faults can have an identical behavior, and say a single pattern is sufficient to detect the other node fault also. So only one fault from that equivalent set is sufficient to be simulated and generate the patterns. So with this, we go to the next concept of fault collapsing. So we remove the other equivalent faults and keep just a one fault and proceed for the simulation and generate the test pattern. So with this, we will have reduced the number of faults. So hence the test, like we said, we need this input. This also we have to generate algorithmically. Like this input, this has to be generated. So the time to generate this input will now go down because number of faults has also come down. Okay, so now we will have an example of a single stacked fault model where we say a node is going to be permanently stuck at 0 or 1. So this models the permanent hard faults. So it is going to be for infinite time duration, always at 0 or always at 1. So now from the previous example we had n has 9 So the number of single fault, we saw it's 2 into 9, it's reduced to 18. Now let's see what is the number of collapsing fault for that. The formula is 2 times PO plus FO plus G1 minus N1. This is the number of inverter. This is the gate input, number of gate input, and this is the fan out step, so number of fan out step, and this is the number of primary output. So with this, can we say what is the number of collapsed faults of the previous? So we have one primary output. Okay, so now two more terminologies. We have something called as primary input and primary output. So if we consider a circuit, okay, I have an AND gate. This is my complete, say, an IC, and outside I have an access to this A, B, and C. These are the two inputs, this is the output. So we call this inputs as primary inputs and this output as primary output. Okay, so now we have only one primary output plus the fan out branch. Here any fan out branch. This is one such fan out stem. So we have one fan out branch plus gate inputs. This is 2, 3, 4, 5, 6, 7. So total 7 inputs. And we have one inverter. This gives 2, 4, 4 plus 7 is 11 minus 1 it is 10. From 18 we can have reduced to 10 fault site. So this gives a reduction of around 50 to 60%. So this concept of the fault collapsing typically reduces number of the stucket fault by 50 to 60%. So further we have something similar concept for transistor level, where this is for gate level stuck at please mention fan out GIN. Sorry, I didn't get it. Fan out GIN. This is one such fan out branch. This one I am considering as one fan out stem. So I have taken F0 as 1. Is it clear? This is coming branching out to 2. So this is one of the fan out stem. So I am considering F0 as 1. So for the transistor level, we can have a concept of stuck short or stuck open, where a transistor is always open or a transistor is always having conducting path. So next is the bridging fault. Now if we have a, say, a line source to destination, and this is a B line, we have a material which is shorting both of them. So this short can cause a bridging fault, which can be of wired and or it can be dominant. That means, say, line B dominates over the line A. Means, say, I can represent this AS. This B, if it is dominating, it is going to be going to be the output of A destination as well as the B destination. Or here again there can be a combination of AND or, so we can also have a fault with dominant AND or. Now this wired AND, between this resistance or this material can do the function of an AND gate and give that output to the destination. So this is the wired AND operation, whereas this can also perform an OR and give into a wired or base defect. Why those faults are called collapsed? Okay, and the concept of fault collapsing and equivalence is that, say we have some a set of, we identify that say F1, F2, F3, F4 are equivalent fault. So we just pick one fault, say F3. If we can generate a test pattern for this, it is sufficient to detect all these faults. That is the concept of fault equivalence, collapsing, and fault dominance. No, they are not redundant faults. They are equivalent faults. Say, for example, I get an output 0 here. So I apply 0 here, 1 here. This pattern can detect a stuck at 1 fault here, stuck at 1 fault here, stuck at 0 fault here. Now, for example, I want a 0 here, I get a 0 here. This can detect the stuck at 1 fault here as well as here. So I can say that this, say F1, F2, both F1 and F2 are equivalent. It's having the similar behavior. Like now the vector to detect this is sufficient to detect this also. Proof of multiple faults. Like for this, they are asking the proof. This is like the types of two types, equivalent and collapse. But how do we explain collapsed one? Yes, the collapsed one says that any one of this equivalent one is sufficient to like test it. Like if we can remove all the equivalent faults, now I just insert a fault here and run my algorithm to generate the vector. So it is sufficient, no need to generate the vector separately for F2. So because they are equivalent, I can remove them and I can generate a collapsed fault set. So is it clear? Okay. So proof of multiple faults, I didn't understand your question. Is you want the proof for this or for this statement? This statement, it is like the formula 1. Okay, this proof I don't have. This comes with the permutation and combination of multiple faults. So proof I don't have. This -1 is for the fault-free circuit, and how many combinations you can generate. So with that you get this number raised to the power n. Okay, so now the next fault type is the delay fault or the crosstalk. Again, in delay, we have two types of delay faults. Generally, we will discuss in the later classes. That is path delay fault and the transition delay fault models. So, path delay usually considers the cumulative propagation delay. And in the delay testing, we need two vectors. We need two test vectors. That is, one vector will just like say I have this transition, and again we have to capture that transition. Is the section recorded? Yes, the section is recorded. So we need two test vectors. First is to activate that delay effect and the transition. So we need to capture this transition. So we need one vector, two vectors. So there is another concept of crosstalk where delay or the glitches that can be caused because of the crosstalk between the two wires. So it can be because of the inductive, that is the inductance and the capacitive coupling between the lines. So next comes the memory testing where we have pattern sensitive or the coupling faults. So if we consider a memory, it's like bit organized if we consider it. So every this square can store one bit. So now, for example, this location was already having a 0, considering it, and for example, some program writes 1 surrounding to it. There is some fault because of this neighboring written as 1. This 0 is now changed to 1 because of this neighboring ones. So such faults we call as the pattern sensitive faults. Because of this pattern bit getting written by some other code, the initially written 0 is now changed to 1, which is a faulty value. Like which is causing an error. The content of the memory cell is affected by the this neighbors. So this is like the contents of this is the memory sensitivity fault. Content of the memory cell is affected by the contents of neighboring cells. Now we have again another type of fault, which is the coupling fault. Like I write a 1 here, it doesn't allow me to write a 1 here. So, sorry, sort of some effect between these two cells. So it's like a transition in the content of one memory cell causes a change in the content of the another memory cell. So like I wrote a 1 here. Initially, if it was a 1, it may changed this to 0. Some effect between the two cells. So such faults are called as the coupling faults. Is transition in contents of one memory cell causes change in contents of another cell. And this pattern sensitive faults are like for this memory with like high density RAM cells. Now the general testing, just I'm giving the name. We use a test called as March test to detect such faults. Now what is the March test? It is like this is a memory cell if I consider. I write one, I read this one, I read this one, then again I write a 0, I read this 0. So some pattern of read and write operation we perform. So we have different versions of this March test, and this is called as a March test, and this is for the memory faults. Okay. With this, we will go for some terminologies. So the overview of VLSI test technology. We already said that we want to apply the test stimuli to the circuit under test. So we have a automatic test equipment. So which stores this test pattern and which will be applying it to the circuit under test. So this is the automatic test equipment. Now how we will get that patterns? We have an algorithmic way of generating that pattern called as automatic test pattern generation. And now, so say I have one pattern to know which are the faults it is getting detected. So we have something called as fault. We perform something called as fault simulation, which means like we apply like which emulates the fault model in the circuit under test, and this is performed in the software and applies this test vector, and we can determine the coverage. So it can be a fault coverage or the test coverage. This can be done in different methods, such as to reduce the simulation time, we can perform it parallel. We have other types called as detective fault simulation, concurrent fault simulation. So this is to emulate the behavior of this fault and the test vector in a software to know the fault coverage or the test coverage. So again, we have two terminologies, fault and test coverage. So next we have something called as DFT, which is designed for testability. Say now I have a IC. If this here I have a deep inside an AND gate. We said 0, 1, 0. This pattern, if we have, we can detect certain faults, say F1 fault. Now to get this value to 0, we can't control this directly. We have just only access to these pins. So it has to come from deep from this sea of the gates. So if it is difficult to control this value to 0, we have certain circuitry added to make this value to 0. So we add certain circuitry in the design, and we say here I want to make it as 0. That means I want to control that value to 0, and I want to observe a 0 here. So I want to observe this say this output. So such things, this we called as the observability or controllability. So DFT are the added circuitry, test circuitry, and which is to improve the controllability and testability or the observability. So this circuitry is incorporated inside the design itself. So generally, so again in this we have three approaches of DFT. One is the ad hoc technique. Each technique has its own advantage and disadvantage. That structural based technique which has say scan design, which can be both scan and boundary, and built-in self-test. So just we will structural DFT is the one which had the scan based architecture which are added. So it is to get the controllability and observability of the internal states of the internal states, and the scan design is the most popular one. So again we have another terminology called as scan design. We will discuss this. Scan is the most popular DFT approach. So in the testability analysis, we said two concepts: controllability and observability. How difficult it is for a node to set to a particular value, and how difficult it is for a node for us to observe a particular value of the node. So just I will write the definition for this. And everything can be set from the primary input, and for everything to observe, it is from the primary outputs. Now, this is the structural method, and built-in self-test is usually used when the circuit is in functional. Like, yes, I just briefly described the other two also, other two methods also. The best, which is the built-in self-test. Now, say I have an IC, which is now completely in the application. So there will be certain logic which will generate the test patterns, and certain logic which can compare this response and say whether it is having any fault or not. This, if for example it is say a mobile phone, we just boot on this mobile phone, it applies some patterns and it will be saying whether it is having a fault or not. So it is used to say for on power on self test. And mostly like this is for the in-field operation. In when we have fabricated, we have an IC completely packaged, fine in the field, in the operation, and we perform the testing either at the boot on or uh, whenever the system is ideal. In scan design, why flip-flops are converted to shift register during testing? Okay. I think we have slides. I will discuss that. So the scan flip-flops, we have some test mode pins which are scan enable, scan input, and scan output. So this is a scan output, scan input, scan enable. We normal D flip-flop. We add a multiplexer. So in the normal operation, when we are not selecting the scan mode, we get the combinational output through the flip-flop to the output. Now, if we select the scan input, I can control this value or this value. Like, say, I want somewhere here to apply a 0. I apply a 0 and Si is equal to 1. I get a 0 here, so it can be applied here. So, similar way, if we want to have a value here is 0, I want to see these values at the output of this. I can select this and view. So this is how a flip-flop is converted into a scan flip-flop and the operations of the scan flip-flop. Test mode and functional mode. So if I want to set a logic 1 here, I want SI to be 1, SE to be 1. Okay. So I think everyone agrees with this. Now if I want to observe D equal to 0 here, we set SE equal to 0. So this way we can capture the value as well as apply the value, like both observability and controllability is provided by this scan flip-flop. Now, if I have say 10 flip-flops, if I don't connect it as chain, I will have 10 scan out, 10 scan ins. For an IC, we have certain number of pins only we can have it. So we cannot go on increasing the pins for an IC. So is your question clear? In scan design, why flip-flops are converted to shift registers during testing? If I don't have convert this, then this should be at the output. Input. This also should be at the input. This, and again this should go to the output. So I will have for the 4 flip flops, 4 scan inputs, 4 scan outputs. So another easy operation is to connect it as a shift register, so that one output and one input we have. And through this one input, we can apply the required values, shifting. Say I want 0101, I just shift in. This is a very high power pattern. Say I want this as one of the vector. So I apply and shift in. Now I can launch this, which will be applied to this combinational logic. This combinational logic, say it gives 111. I can just bring it back to this flip flop and I can shift out. Previously we shifted in the patterns and we are shifting out the response now. So this is how the scan flip flops connected as a shift register can be used. So why this flip flop or the scan chain? If we consider this node to be stuck at 0, what will be the required pattern for detecting this fault? Then if I want to test only one point, how should I do that? I think now I'm giving an example of testing just a one point. And here I have a flip-flop, 2 flip-flops connected as a scan chain. So can you tell me what should be the value at the node E? So first we have a concept of exciting this fault. We have to trigger this fault. So what should be the value at the node E? So that I have a good value of 1 and my faulty value goes to 0. Now with this, what should be the A, B, C and D values? Yes, 1. So A, B should be 1. So now this, if it is coming in from a deep, some combo logic, to setting this node value to 1 is the difficulty, the effort will increase. And to measure such efforts, we have some metric called as scope analysis, which tells how difficult a node is going to be for controlling and as well as the observing. So now I can use the scan path. So this one is called as fault sensitization, and coming back till the primary input, we call them as the line justification. So now I apply through the scan enable and select this scan path. So now I got this faulty value, like fault free should be 1, faulty should be, okay, I think this has, yeah, this has some error. This is correct. Fault free is 1, but faulty is 0. Now I want this value to be seen either at primary output, and this scan output we also call as pseudo primary output. So either at pseudo primary output or the primary output, we want to observe this 1 bar 0, which is the fault free versus by the faulty value. So now we can shift out this value, which is will be captured by this flip flop by selecting the G, and this one is called as the fault propagation. So in this way, I think your question is answered. What if we want to test only one point? So how can we do that? Is your question clear? Is your doubt clarified? Yeah. So now we have seen these 3 steps where we set fault sensitization, fault propagation, line justification. This is the terminology used for the ATPG, automatic test pattern generation. This also we will discuss in the later classes. So just to make you familiar with few terminologies. To excite this fault, we set the fault sensitization step, and from this point coming till this primary input, we said it is line justification. Propagating this to the primary output or pseudo primary output, we called as fault propagation. What if I want to sensitize multiple fault? How to generate pattern for that? Yes, the difficulty is that multiple faults you have seen it has for a smaller circuit itself we have so many multiple faults. So that's one thing, and multiple faults again similar approach of sensitizing, and we have to generate the fault. So if we can just assume that, say here it is a stuck at 0, here it is a stuck at 1, If both the lines are stuck at 0, 1 1 should excite the fault. Now this 1 1 should be giving the output 1, but because of the fault it gives 0. Now this will be equivalent if either F1 is stuck at 0 or F2 is stuck at 0. That's why we came to the concept that we came down from multiple to single fault model. Is your doubt clear? Okay, now let's solve some questions from the previous year assignment. So let us consider a chip and say that a particular portion is getting heated up to a temperature T1, another to T2. So what is the fault or the defect or the error that we are getting? Okay, what problem arises when different parts of a chip are heated differently? So can we say that because of heating we are going to get a short? Yes. It's getting heated indifferently, so we can't say it is going to form a bridging defect. Neither it is going to cause an open, so or which will result in high or high impedance point. Because of heating, there may be a difference in the delay. So the answer is C. The next question, at which level we can rectify a defect with minimal effort? At the lower abstraction level, the effort will be minimum. So yes, at the device level, the effort will be minimum. So what is the basic difference between verification and testing? Yes, option D. Verification targets design errors and corrections are made prior to fabrication, while the testing is a post fabrication process which targets the fault introduced during the manufacturing. Next question, in a system level operation, the system availability is given as the mean time between failure is 105 hours. What is the mean time to failure of that system? So for this we have one formula. The system availability is mean time between failure divided by mean time between failure plus mean time to failure. So if we take this as system availability 0.9846, 105 hours. The answer is in hours, so I can just keep it in hours. 105 plus MTR. So this will be 105 divided by 0.9846 minus 105, which is equal to 1.6422 hours. So yes, the correct answer is option B. So with this, going to the next question. With a given multiple fault model, a circuit has 6 possible fault sites. Each fault can be of 3 types. So they have given 3 fault types. So the K is 3 here. And what is the number of fault site? Which is 6. So what is the number of multiple fault according to this model? The formula for the number of multiple fault site is K plus 1 to the power n minus 1. So it is 3 plus 1, which is 4 to the power 3 plus 1 to the power 6 minus 1, which is 4 not 6 minus 1. Yes, option D. So what will be the answer if it is, if we consider the number of single fault? It's just n into k. Yes, 3 into 6, it is 18. See from how much, like from 4095, we have come down to 18. And now if the circuit is given, then now we can again show how it comes down using the concept of the fault equivalence and the fault collapsing. But still, from this, so the answer is D. Next question. Calculate the number of collapsed fault for the following circuit. And the formula for that is two times number of primary output plus the fan out stem plus G1, which is the gate input, minus inverter, number of inverters. So for this circuit, what is the primary output count? 1 and 2. Two primary outputs. What are the fan out branch? And this is one fan out branch. This is another fan out branch. This is the third fan out branch. Again, a fan out branch. So total 4 fan out branches. Next, what is the gate input? Take circular. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 inputs and number of inverter, 2 inverters, 1 and 2. So if we substitute 2 times 2 plus 4 plus 14 plus not this minus 2. It is 6 plus 6 into 2, 12, 12 plus 14, 26 minus 2, which is 20. Pick the correct statement from the following. So the stuck short fault in transistor means the source and drain connections are shorted. Yes, this is true. The transistor is, when the gate and drain are going to be shortened, means that transistor is always going to be in the conducting state. And stuck open means the transistor is not going to conduct. So it's unable to conduct, that means it is in the open state. So this is also correct. So stuck open fault is detected by applying two patterns. Okay, so we will discuss how we can detect this short fault as well as this stuck open fault also. So if, say for example, I just consider one inverter. Now this is going to be always on. At some point of time when I am going to switch from 0 to say 1, in this transition there will be a chance of going this the current going high and then settling back. But when there is such a defect, okay, when the short path will come, let's consider if this is now, if this is going to be always on, in this place when there was it has to be like off, the current will remain high. Just this will be the IDDQ current. Because here the, let's say P1 N1, here the P1 is going to be on, here the N1 is going to be on. So because of the fault, P1 is also going to be in the on state. Because of that, there is going to be a current in the short path. And this is the high current, this transition current. This high current, when we measure, we can detect such short faults. This is the step. So this method is called as IPVQ based testing. Whereas if we have a transistor which is open, we need two patterns. First vector to initialize it so that we excite the fault. Next vector to detect the fault. So this is also correct. So the correct answer is all of them. Now, next question. Considering a single fault model, a circuit has 4 fault sites. Following are the patterns needed for each of the respective fault. Find the necessary vector from the provided patterns. So, what is the necessary vector from these patterns? Could you please explain the previous question? Yes. Is this stuck short fault testing method clear? Testing using an IDDQ based method. Okay, so now I will just show how we do that for the stuck open fault. So now say if there is a fault, this is a PMOS, this is an NMOS, this remains open. So for that, first I need a vector. Just I charge this node. I apply a 0 here. I charge this node to VDD. Now next vector I apply 1 and try to discharge through this node. But as it is open, it will not have this path. So this cannot be discharged to from VDD to ground. In this way, we can deduct this fault. So we need two vectors. First vector is just is applied to excite this fault, and next one is used to deduct the fault. So this is just an example with an inverter, so that now this VDD doesn't have a path to go and to discharge to ground. Okay, so now next question. So what is the necessary vector? Now this F1 is a fault, like one of the fault site. So if I consider there are some logic gates, I'm just saying what is this. This can be F1, say this can be F2, this can be F3, say this can be F4. Just for example. Or instead of this, F2, F3, F4. So these are the fault site. Now to detect the F1 fault, we need all these vectors are sufficient vectors. Similarly, if to detect the F2 fault, these are the vectors. Now what is a necessary vector is that if we take this vector and if I remove, say, from this all this list, if I remove this vector, I cannot detect F3 fault. So such a vector is a necessary vector. Clear? So if we consider F1, F2, F3, F4, it's just an example circuit where each F1 represent one fault site. So there are total 4 fault sites. And this vector means if I apply 1 0 0 1 1 to my circuit, I can deduct this F1. And if I apply this vector, I can even deduct F2. I can also deduct F3. Similarly, I have a choice. Again, I can have some other vector that I can deduct. Say, I apply this vector, I can deduct F4 also. But this is the vector. If I remove this vector, say, uh, 5 ones, we can't deduct F3. The fault if 3, to detect this fault, this vector is the necessary vector. So we can't remove this vector. For example, by any chance I say that okay, this vector is going to consume a lot of power, I remove this. Still there are vectors which can detect all the fault sites. But if I remove this, F3 will remain undetected. So it is a necessary vector. So not the F3, this 5 ones is the necessary vector. Clear? Map the relevant elements of the following column. Uh, what are the pattern sensitive faults? It is caused because of the memory cell and affected by the neighbors. Option C. Is it? So this is crosstalk was because of an inductive or capacitive coupling in the next line. So and the coupling fault was again with respect to the memory where transition in one cell was affecting the next cell, and path delay we said is a cumulative effect. So it's a option D. So next question is why a dock multiplexer insertion is often not acceptable. So yes, this one alone we discussed the built-in self-test, which is the best, and also we have discussed the structural based testing where we have the common method is the scan based method. Another is the ad hoc method where we insert a multiplexer to do both the controllability as well as the observability. So say we have the controllability of the test point, we just insert one multiplexer. So here we have the test data input. Again we need to select it, so it's between the test mode and the functional mode and normal system data. And this is that internal node to be that we want to control. Similarly, to provide the observability to a node, we have a primary, take that to the primary output and the normal data and the internal node that we want to observe. So this now we are going to insert in a place which we want to observe or control. So we are, if it is in the critical path, we will affect the critical path delay. So it may affect the critical path delay of the design. So option B is the correct. Is this clear? Next question. Select the correct statement from the following. How are we observing the output with the mux? This output is a primary output which we can see from the outside of an IC. So any node which we want to observe, we apply to one of the input. During the test mode, we can select it. The other one will be the normal output. Now in the test mode, if I select this, we can see it through the primary output pin. Clear? So, which of the statement is correct? We have said that this ad hoc based method will affect the critical path. So the structural DFT which we use, like convert the normal flip flop to scan flip flop, we do it during the design phase itself. So that time we take into the account of all the delay uh, acquired by that multiplexer addition. So that's why we prefer the structural testing compared to the ad hoc based method. Is it fine? So now further we have some concepts of testing the IO also, and the which where we use the boundary scan based methods. Also for the in-field operation, we said we will be using some methods known as the built-in self-test. Again, the built-in self-test, we have two types, one for memory, so M-based, or for logic, L-based. So now this we have seen how it is getting exploding with the number of inputs and the number of gates. Now, if I have just an AND gate with say A and B input, 2 to the power n, which is say 4 combination, is, is the only possible combination required to test the complete AND gate. Then can we say that even we can test a circuit exhaustively? Is it possible to test a circuit exhaustively? Why not apply the complete test bench to the circuit? If we are if this remains low, then generating the test pattern is equivalent to the complete test truth table of that circuit. Any answers? Can we test any circuit exhaustively? Yes, only if the logic is small. So now if we say any 64-bit circuit, then it will have 2 to the power 64 total combination. So here the testing with the complete truth table will become difficult. And also when it comes to delay testing, 0 to 1 transition, 1 to 0 transition, 1 to 1, 0 to 0. The number of transitions also goes on increasing. That's why we come to a sample of fault and how to detect that fault. Even one vector, we have already seen that in this example, that one vector is able to detect multiple faults. To detect, say, F1, F2, F3, F4 fault, we can say that this pattern and this pattern will be sufficient. Uh, any doubts? Any questions? In case of AND gate, what is the minimum number of vectors required to test? Uh, yes, that we can see. So this has total 3 fault site. Um, if we consider that it is sufficient to test the primary inputs, then A stuck at 0, stuck at 1, B stuck at 0, stuck at 1 should be sufficient. Now for that pattern should we say 0, 0. Should be covering this both the patterns, and 1 1 should have covered this both the vectors. So I'm just doing it. I hope this should be sufficient. Can you try whether this is able to detect all the 6 faults? According to this, I hope 0011 should be sufficient. Can you explain the multiple fault formula? Why are we not just keeping n into k? When we have say 3 fault site or number of fault site k into number of the fault, I think I changed it. K is the number of fault type and n is the number of fault site. So this will be each and every node having one fault at a time. Now if we have multiple fault, then we have the various combination of faults. Either two node can be stuck at 0, or two node can be, like one node can be stuck at 0, another can be stuck at 1. So there we have the formula of k getting rise to the power n minus 1. This is for the fault free circuit, where one combination will be including the circuit where there is no fault, for removing that minus 1. And that's why we have a formula with k to the power n. That many combinations of possibilities are there. Clear? Y plus 1. this plus 1 for the combination. Say, let's just take this one. Here we have 3 fault side. So n is equal to 3. If I consider stuck at 0 and stuck at 1, so that time k will be 2. So in that case, what will be according to the formula? 3 raised to the power 3 minus 1, which is 8. Now let's just do this math because manually. Either all the 3 can have a fault, that will be 1. Or just this two having a combination of fault. Like all the 3 can be stuck at 0, or all the 3 can be stuck at 1. I think you can try with the small circuit and then see how many combinations are you getting. Multiple fault site manually for this AND gate. Then we can discuss. So coming to the next question, can you please explain it the question that you have shown before? Which question? This question. Question number, please. Question number 4. Yeah, I have just directly used the formula. System availability is the mean time between failure divided by mean time between failure plus mean time to failure. Okay. That k plus 1, can you try for an AND gate, or we will discuss it in the next class? Because I am also not very sure why it is k plus 1. But it's raised to the power n because we need to have the combinations, like for all the combinations. I think for multiple structured faults, there are few other formulas also. So I think we can discuss that in the next class. This So let's just summarize whatever we have seen. So today we just discussed few of the terminologies, what is testing and verification, and in the complete ASIC design flow where actually this testing is used and where the verifications are used, verification is done, and what is the defect, fault and error. And we have come to few fault models, and with that we have seen the fault model of multiple fault model, and we came that even if we have a good fault coverage for the single stucket fault, a single fault model, it implies it will give a good fault coverage for the multiple fault also. So will there be recordings of this section made available for future reference? Yes, the recordings will be shared in the like uploaded in YouTube, and the link will be shared, and even the slides will be uploaded. Ma'am, can you please show slide for from problem 5 again? 3, 4, 5. Problem 5. Actually, multiple stuck fault model is not that much considered in practice. There is I just want to try. There is one formula where we have say stuck at 0, stuck at 1, and a good circuit. Plus 1 is for fault free circuit, minus 1 is for fault free. So the number of faults at if it is 3, it is like 9 minus 3 2s are 6 plus minus 1. Not this 3. Okay, reference from VLSI book. Plus 1 is for fault free fault, minus 1 for fault free circuit. Yes, that minus 1 is for fault free circuit. So K is the number of fault types and plus 1 is for good circuit, I think so. Is it? Yeah. I am also thinking the same thing. Like K raised to the power n to give the number of combination, and minus 1 this is to remove the fault free circuit. This is to show that we have 1 to K types of faults. Then we need the circuit in the combination we can also have a good like good value or like a fault free value here. Like in the n node can also be fault free. So we need a plus one. Is it? I think that's the reason. Correct. Let's just discuss that number of multiple faults also. Yes. So it's like k. So we said say stuck at 0 or stuck at 1. So a node can have either stuck at 0 or stuck at 1. So it is 2 plus 1 to indicate in that n nodes a node can be even fault free. But in this combination there will be a one circuit which will be completely fault free. We will remove that circuit. So so yes, the minus one is for the complete fault free. Yes, I think now this formula is also clear to everyone. Any other doubts? If no other doubts, we can meet next week, Tuesday, same 6 to 8 p.m. So I will end the recording.